Hello everyone, welcome to this talk. My name is Jun. I'm a solutions architect in Viverica.
My name is Nico and I'm head of solutions architecture at Viverica.
As we all know, Apache Flink is very good at low latency stream processing. However, as Flink is a generic stream processing framework, it can be used in many different use cases. As a Flink application developer or class administrator, you need to find the right gear that is best for your application to avoid driving a luxury sports car while only using the first gear.
Our team has been doing Flink consulting, training, and support for many users and various use cases. In this talk, we will present low latency optimization best practices that we've collected over the past years. So if you're looking for ways to improve the latency of your Flink applications, you're in the right session.
This talk is organized as follows. We first talk about what we mean by latency and how we measure it. Then we present a couple of low latency techniques divided into two groups. The first group is about direct latency optimization. This will be presented by me. The second group covers optimizing throughput in order to improve latency. I leave this part to my colleague Nico. For each optimization technique, we will clarify what it is, when to use it, and what to keep in mind when using it. We will also show experimental results to support our statement. When talking about latency, different people may mean different things. Latency markers in Flink measure the time it takes for them to travel from each source operator to each downstream operator. As the latency marker bypass the user function in operators, the measured latency don't reflect the entire end-to-end latency, but only part of it. Flink also supports to track the state access latency. It measures the response latency when state is read or written. You can also manually measure the time taken by some operators or get it with profilers. However, what users care very often is the end-to-end latency, including the time spent in user functions, in framework, and when the state is accessed. This is exactly what we are going to focus in this talk. There are two scenarios here. If a pipeline does a simple transformation, there's no timer or other complex event time logic. For example, the pipeline produces one output event for each input event. In this case, we measure the processing delay as a latency, that is T2 minus T1, as shown in the diagram. When complex event time logic is involved, for example, timers, aggregation, and windowing, etc., then it's not that straightforward. In this case, we measure the event time lag, that is the current processing time minus current watermark. Basically, the event time lag gives us the difference between the expected output time and the actual output time. In either of the two scenarios, we capture a histogram and show the 99th percentile of the end-to-end latency. You might have already noticed the latency we measure here includes the time an event stays in the source message queue, for example, Kafka. The reason for this is that it covers the scenario where a source operator is backpressured by other operator in the pipeline. The more the source operator is backpressured, the long time the message stays in the message queue. So including the times event stays in the message queue in the latency gives us how slow or fast a pipeline is. Now that we know what latency to measure, let's move on to the low latency techniques. As mentioned before, some techniques optimize latency directly, others improve latency by optimizing throughput. Each of these techniques can be as simple as configuration change or require code changes, or both. We have created a Git repository containing the example jobs used in our experiments. You can check the repository for details. A disclaimer here. All the experimental results we will show are specific to those jobs. Your job may show different results depending on where the bottleneck is. The first technique is to allocate enough resources. Flink has metrics to indicate whether an operator or subtask is busy or not. If some operator in your job is 100% busy, it will backpressure upstream operators. the backpressure may propagate up to the source operators. Backpressure slows down the pipeline and results in high latency. If you scale up your job by adding more CPU or memory resources, or scale out by increasing the parallelism, your job will be able to process events faster or process more events in parallel. The latency can then be reduced. We recommend to have the average load below 70% under normal circumstances to accommodate the load spikes that come from input data, timers, windowing, or other sources. Obviously, you should adjust based on your job resources, usage pattern, and latency requirement. Keep in mind, in case of scaling out with high parallelism, your job must be able to make use of the additional resources. For example, you should not have a fixed parallelism in your job code. You should not bottleneck on source. Input stream must be partitionable by keys such that it can be processed in parallel. And you should have no data screw, etc. Obviously, adding more resources may result in an increased financial cost, especially when you are running jobs on the cloud. This slide shows the experimental result with a windowing job. As you can see from the graph at the left, when the parallelism was 2, the 2 subtasks were often at 100% busy. After we increased the parallelism to 3, then the 3 subtasks were around 75% busy only. As a result, the 99% percentile latency is reduced from around 3 seconds to 650 milliseconds. The second technique is to use applicable state backend. When using the file system hashmap state backend, the state objects are stored in memory and can be accessed directly. In contrast, when using a RocksDB state backend, every state access has to go through serialization or deserialization process, which in addition may involve disk access. So if your state size is very small compared to the memory you can allocate to this job, and your state size will not grow beyond the memory capacity, you can consider to use a file system state backend instead of RocksDB, and set the managed memory to 0 if not needed. Actually, since Flink 1.13, you can always start with the hashmap state backend. You can seamlessly switch to RocksDB state backend via save point when the state size increased close to your memory capacity. Note that you should closely monitor the memory usage and perform the switch before OOM happens. Keep in mind, heap-based state backend use more memory comparing to RocksDB due to its copy and write data structure and Java's on-heap object representation. Heap-based state backend can be affected by garbage collector, which makes it less predictable. So you may get high latency. So there's no support for incremental checkpointing. You should measure the difference before you make the switch. As you can see from the experimental result shown on this slide, by switching to hashmap state backend, we reduced the obtained state backend further down to 500 milliseconds. Depending on your job's state backend state access pattern, you may see large improvement. The graph on the right shows the GC impact to the latency. Next technique is to emit watermark quickly. When using periodic watermark generator, Flink generates a watermark every 200 milliseconds. This means that by default, each parallel watermark generator does not produce watermark updates until 200 milliseconds have passed. While this may be sufficient for many use cases, if you are fighting for the sub-second level of latency, you could try to reduce the interval even further, for example, to 100 milliseconds. But keeping in mind that too frequent watermark generation may also degrade the performance because more watermark must be processed by the framework. After we reduce the watermark interval from the default 200 milliseconds to 100 milliseconds, we reduce the latency further to 330 milliseconds. Next technique is to flush the network buffer early. Flink uses buffers when sending data from one task to another over the network. Buffers are flushed and sent out when they are filled up or when the default timeout 100 milliseconds have passed. Again, if you are fighting for sub-second level of latency, you can lower the timeout to reduce latencies. Note that too low buffer timeout may reduce throughput. By reducing network buffer timeout from the default 100 milliseconds to 10 milliseconds, we further reduce the latency to 370 milliseconds. So overall, by applying the 4 low latency techniques we have presented so far without any code change, we have managed to reduce the latency from around 3 seconds to 375 milliseconds. Since our stream has an out of ordinates of 250 milliseconds, we cannot reduce latency to less than that. With 375 milliseconds of latency, we are quite close now. Next technique is to spread work across time. Unlike the previous techniques, you need to change your code to do it. When you use timers or do windowing in a job, timer or window firing may create load spikes due to heavy computation or state access. If the allocated resource cannot cope with the load spikes, the timer or the window firing will take longer time to finish. This resulted in high latency. To avoid that, you should change your code to spread out the workload as much as possible, such that you don't accumulate too much work to be done at a single point in time. In case of windowing, you should consider to use incremental window aggregation with aggregate function or reduce function. In case of timers in process functions, the operator executed in the onTimer method should be optimized such that the time spent there is reduced to a minimum. If you still see latency spikes from, for example, the workload from a single key, or if you need to collect the event in a well-defined order to perform a certain computation, you can consider to add a new upstream operator before the current operator and apply this technique there. One thing to keep in mind, when you spread out the work across time, you should consider not only computation but also state access, especially when using RocksDB state backend. Spread out one type of the work while accumulating the other may result in worse latencies. To show the latency improvement of this technique, we use the same windowing job as before and run it with and without incremental window aggregation. As you can see from this slide, by using incremental window aggregation, we reduced the latency from 1.7 seconds to 720 milliseconds. Next technique is to access external system efficiently. When you're interacting with external system like a database in a Flink job for data enrichment, the latency in getting response from external system often dominates the overall latency of the job. In this case, you should consider to use the Flink's async I/O API. For example, async data stream unordered wait or ordered wait. The difference here is with ordered wait, you can leave the output. You can have the output event in the same order as the input event, but this comes with some latency overhead. With async I/O, one subtask can handle many requests concurrently and receive responses asynchronously. The waiting time for the responses is then amortized over multiple requests. The latency can then be reduced. To use async I/O, the client for your external system needs to support asynchronous request. If it does not, you can also use a thread pool of multiple clients to handle this synchronous request in parallel. You can also use cache to speed up things if the database is not changed frequently. In this experiment, we simulated an external system which returns responses within 1 to 6 milliseconds randomly, and we catch the response in our cache for 1 second. By using async I/O, we reduce latency from around 600 milliseconds to 100 milliseconds. If you are enriching a streaming of events with an external system that is frequently changed, the changes can then be converted. The changes can be converted to a data stream. Then you can have another option to use connected streams and co-process function to do the streaming join. This usually can achieve lower latency than the per record lookup approach. An alternative approach is to preload external data into the job, but a full streaming join can usually achieve better accuracy because it does not work with the stale data and can take event time into account. For more ways of streaming enrichment and their pros and cons, we recommend you to check out our webinar linked on these slides from my colleague Konstantin. This technique is about tuning checkpointing. Checkpointing has two things to do with the latency. If you are working with transactional sync with exactly one semantics, the output events are committed to the external system, for example Kafka, only upon checkpoint completion. In this case, tuning other options may not help if you don't tune the checkpointing. So to reduce latency in this case, you want to find ways to have faster and more frequent checkpointing. To have more frequent checkpointing, you can reduce checkpoint interval, reduce minimum pause between checkpoints. You can also use concurrent checkpoints. But keep in mind, the concurrent checkpoints introduce more runtime overhead. To have faster checkpointing, you need to reduce the checkpoint duration. To achieve that, you can turn on RocksDB incremental checkpointing to reduce state stored in a Flink. For example, clean up states that are not needed anymore. Don't put cache into the manual state. Store only necessary fields in a state, etc. You can also try to tune checkpoint alignment time to reduce checkpoint duration. I will share more details on this in the next slide, because checkpointing alignment can impact latency even if you are not using exactly one semantics. Another option is to not use exactly one sinks, but switch to at least one sinks. The result of this is that you may have duplicated output events. So this requires a downstream application that consumes the output event of your job can do deduplication. The second aspect that relates checkpointing to latency is that during a checkpointing alignment, an operator blocks the event processing from the channels where checkpoint barrier have already been received in order to wait for the checkpoint barrier from other channels. So longer alignment will result in high latency. There are different ways to reduce checkpoint alignment. First, you can consider to improve the throughput. Any improvement in throughput helps processing the buffer sitting in front of the checkpoint barrier faster. The second option is to scale up or scale out, same as the first low latency technique we presented before. This has two effects. It reduces back pressure because it increases processing power. And with the increased parallelism, writing checkpoints to remote storage can also finish quicker. As a result, checkpoint duration is reduced. The third option is to use unaligned checkpointing. In this case, checkpoint barrier don't wait until the data is processed, but skip over and pass on to the next operator immediately. Skipped over data, however, has to be checkpointed as well to be consistent. Flink can also be configured to automatically switch over from aligned to unaligned checkpointing after a certain alignment time has passed. The fourth option is to buffer less data. You can reduce buffer data size by tuning the number of exclusive or floating buffers. With less data buffered in the network, the checkpoint barrier can arrive to operate quicker. However, reduced buffers have an adverse effect on throughput, and it's just mentioned here for completeness. The recently released Flink 1.14 introduced a new feature called buffer debloating. It can dynamically adjust the buffer size based on the current throughput, such that the buffer data can be worked off by the receiver within a configured fixed duration, for example 1 second. This reduces the data during the alignment phase, and it can be used in combination with the online checkpointing to reduce the checkpointing alignment time. The performance result here is from the Flink's release blog post. By using buffer debloating, the checkpoint duration on the back pressure is reduced from around 80 seconds to 5 seconds when debloating target is set to 1 second. With this, I'm done with the first part of our talk, direct latency optimization. I head over now to Nico for the second part.
In the last part of this talk, I'd like to present a couple of techniques to optimize throughput. But wait, didn't we want to optimize for latency? Yes, we did, but most of the techniques that optimize throughput will also improve latency. And why that is easily explained by the graph as shown, because you will eventually go into situations where your load is spiking. And once you're capped at 100% CPU, other events will be waiting in your pipeline, and that increases latency. If you optimize for throughput, that will lower the overall CPU usage and thus also improve the latency. At the same time, you can also use less resources at normal operations and thus save money. However, some of the techniques that improve throughput will actually hurt performance, so take special care with those. The first technique that I'd like to present is coalescing timers. Think of the following scenario. We'd like to sort a stream of events, and we buffer every event that we see, register timers into the future, and whenever that timer fires, we sort the events we've seen so far, traverse them in order, and put them on the output. So for the scenario that is shown on the slide, the watermark is jumping from 0 to 10, and we have to execute 4 timers. One at timestamp 1, then 3, then 8, then 9. Each of those is sorting the events that you've seen so far and traversing them and putting them on the output. By coalescing timers, we want to reduce the number of timers that are too close to one another. We could do so, for example, by only firing at the nearest multiple of 5, and therefore in that concrete scenario we'd only have 2 timers. One is firing at 5, is sorting it, putting on the output, the other is at 10, and by having less of those sort operations, we do less work in total and improve the latency. You can coalesce timers at any point of time. You can round up to the next full second, 100 milliseconds, or whatever you like. Now, still, we would execute 2 timers, one after another, when the next watermark is coming, and therefore you can also change that slightly, and instead of firing at specific points in time, you would just fire at the next watermark. And whenever that comes, you will do your work, like in that case, sorting, traversing, putting on the output. However, by coalescing timers, you can also increase the latency, which is not what we want. First of all, the coalescing itself. If you only fire timers, let's say, in the next closest hour, then this will be your latency that you might observe. So don't go too far in that situation. Also, if the amount of work that your coalesced timer has to do is the same or even more than the work of the individual timers, then you will also not gain much, and that will hurt latency. So that technique is only applicable for certain situations, like the one that I presented. And in that concrete situation, we're able to reduce the event time lag from roughly 4 seconds down to roughly half a second by coalescing the timers to the closest 100 milliseconds instead of firing them individually. The next couple of techniques all fall under a bigger category of reducing the per event computation overhead as much as possible. And whatever of those techniques apply, the approach is always the same. First, you start by creating a benchmark. That benchmark should run at full throughput. That can be done by either implementing a custom source that generates events as fast as possible, or just put a lot of data, a huge backlog into your existing sources that you use in production as well, like Kafka. And then once you have the data, you establish a baseline. You measure the throughput so that you know whenever you're doing an improvement, whether it's actually improving things or it's making things worse, and how big the effects are. Once you establish the baseline, we go into trying to find individual hotspots, and that you can do by either using the profiler of your choice, or since Flink 1.13, you can actually pretty easily use Flink's very own back pressure monitor, where you can look at the job graph and immediately see where most of the time is spent. And once you identified the task that is using most of the CPU time, you can look into Flink's flame graphs, which you can enable by configuration, and then see the individual bits and pieces of your code that contribute the most to the CPU usage. Once you found those hotspots, you should mitigate them. Try to optimize this part as much as possible, and then you go back into measuring the performance and looking for the next hotspots. In the very first example for doing this technique, we had a job which is initializing an object mapper once an event came in, and that was quite some overhead that was identified by looking at the flame graphs or profiler. And the object mapper is also something that we could initialize only once. We could put this into the open method and then just use the single instance of the object mapper whenever a new event is coming. And by applying that technique, we're able to get the CPU time down from roughly 23% to 16%, and that also has a positive impact on the latency as presented earlier. So in that case, the latency is improving by 10%, but the higher the CPU load, the higher the impact on the latency. The second technique in this category is looking at serialization. So whenever you look at the profiler or the flame graphs, at the very top of the CPU users, you will probably see some serializer. And roughly a year ago, we actually created a couple of micro benchmarks to identify the exact overheads and the exact performance that are to be expected from using different serializers that Flink offers. You can start as low as using the default cryo fallback, which can be improved by registering types with a cryo system that easily triples your performance. You can also try to avoid cryo in the first place and use Flink's fast POJO serializers that roughly doubles the performance again. Or you go even lower and use custom serialization, which can roughly double it again, but increases a lot in the maintenance because you have to maintain your serializers yourself. And then there are also some other serializers that are kind of in between, like Avro or Protobuf, that you can also use and get a decent performance out of them. Just to showcase this in a real scenario, the sorting job is here applied with two different versions of serialization. One is using the cryo fallback, and that one is using 40% of the CPU already. And the other is using Flink's fast POJO serializer, which then only uses 15% of the CPU time. And that reduction in the CPU time also improves your latency accordingly. The third technique in this category that I'd like to talk about is enabling object reuse. If you have a more thorough look at your tasks, you will eventually see that Flink is chaining a couple of the operators that you put into your job together into an operator chain. Inside those operator chains, whenever you pass an event from the output of one operator to the input of the next operator, Flink is doing a defensive copy. So the new operator gets a completely separate instance, and you can do whatever with it. It would never affect the previous operator. You can change that behavior quite easily by setting a configuration parameter or putting this one line of code inside your job, and then Flink will not do a defensive copy, but instead pass your operator by reference. So whenever it's passed from one to the next, you will not do a defensive copy, and that reduces the serialization overhead a lot and lowers the latency, especially during those temporary load spikes that we were talking about earlier. This technique can easily be enabled in the table API, also in the SQL API, and with Flink 1.14, that is also true if you were using the JDBC sync in those two APIs. However, if you were using the data stream API, then you have to take very special care not to buffer any objects inside your own operator when you pass them on to the next operator at the same time. Because whenever you do that, if the next operator is changing them, it will also change the version that you have, and that's probably a bug in your business logic. You can avoid that by passing on copies whenever you need them, but then you kind of back into doing the defensive copies. However, you can only do them in places where you actually store elements and avoid all the others. You could also work with immutable objects, but that's usually a bit difficult to get right with efficient serialization and usually means that you have to write custom serializers. By enabling object reuse, in this concrete example, we were able to bring down the overall CPU usage from 100% down to 60%, and that decreased the latency from 4.5 to only roughly more than half a second. That is a huge gain, not just for throughput, but also for latency. And it's easy to enable. And with this, I'd like to wrap up the talk in itself and give you an overview of the low latency techniques that we've presented. So Jun has been focusing on more techniques that directly affect latency. I've been focusing more on the throughput side of things, and Jun mentioned that you should emit watermarks quickly, that you flush network buffers early, that you allocate enough resources for your cluster in the first place, use the right state backends, and then also tuning checkpointing, both for end-to-end latencies and their alignment. And then he was also presenting techniques to access external systems efficiently and spread work across time. I presented the technique to collect timers, and then also went into techniques that reduce the per-event overhead, starting with optimizing your user code, choosing the right serialization, and enabling object reuse. With this, I'd like to thank you for listening and open this up for further questions from the audience.